How can NASA communicate by radio and telemetry with Voyager 1, which is 23 billion kilometers away? Strange transmissions from Voyager 1 have recently been making the rounds on the tech news networks, while the usual suspects decided to jump to the typical conclusions that there's alien invaders. And the apparent lack of a firm explanation for the strange, some of us have used the occasion to marvel at the fact that the two Voyager spacecraft, already more than 40 years old, are still in full connection with those of us on Earth. Despite having traveled nearly 23 billion kilometers in one of the most hostile conditions imaginable. Moreover, like many NASA spacecrafts, Voyager has exceeded its original design goals and continues to send back vital science data until June. But really, how is that even possible? Voyager's radio, it turns out, isn't magic. It's just really good engineering with a healthy dose of redundancy and a little sprinkle of luck throughout the years. Voyager was envisioned unusually early for a program that defined the post-Apollo era of planetary exploration in many respects. The detailed mission profile arose from the mid-1960s Planetary Grand Tour concept, which was intended to use as alignment of the outer solar system back in the late 1970s. After an initial fueled boost, a probe might approach Jupiter, Saturn, Uranus, and Neptune with gravitational aids before being blasted out on a track that would eventually send it out into the interplanetary medium, if launched at just the right time. The concept of exploring all of the outer planets was too appealing to pass up, and the Voyager program was born, with the Pioneer missions to Jupiter functioning as dress rehearsals. Like all NASA missions, Voyager had a set of primary mission objectives, a collection of planetary scientific experiment project leaders were confident would be completed. The Voyager spacecraft was built to achieve these primary mission objectives. Still, mission planners believed that they would live until their last planetary encounters and give valuable data as they traveled throughout space. As a result, the hardware, both on board and on the ground, reflects that optimism. The Voyager twins were each deployed with the widest dish that might fit into the shielding of the Titan IIIE launch vehicle, notwithstanding the scale differences since the DSN has telescopes of up to 70 meters across. The primary reflector of each Voyager spacecraft's high-gain antenna, or HGA, is a 3.7-meter diameter parabolic dish. The dish is constructed of honeycomb aluminum with a graphite-impregnated epoxy laminate covering. The reflector's skin is flat and precise, with a surface accuracy of 250 meters, which would be required for operation in both the S-band of 2.3 GHz, which is used for downlink and uplink, and the X-band of 8.4 GHz, which would only be used for downlink. The Voyager antennas, resembling their Earth-bound equivalents in the DSN, are Cassegrain reflectors with a frequency-selective subreflector, or FSS, near the primary reflector's target. Incoming X-band waves are focused and corrected by the subreflector, placed in the primary's dish center, where the X-band feed horn is situated. On the X-band, this configuration offers around 48 dBi of gain and beam width of 0.5 degrees. The feed horn is located inside the subreflector in the S-band layout, which is a little unusual. The subreflector's material's frequency selectivity allows the S-band frequencies to pass through and instantly illuminate the primary reflector with a beam width of 2.3 degrees. This yields roughly 36 dBi gain in the S-band. On the Earth-facing edge of the subreflector structure, there's already a low-gain S-band antenna with a much more cardioid emission sequence, but it was only employed for the first 80 days of the project. The transmitters, receivers, amplifiers, and modulators of the radio frequency subsystem, or RFS, occupy 3 of 10 ports on each Voyager's bus. Redundancy is the right approach in the RFS, as it would be in all high-risk space missions. Practically every possible single point of failure has a backup. A design process decision that has verified mission saving in more than one case on both spacecraft during the last 40 years. In addition, each Voyager contains 2 S-band double conversion superhet receivers on the uplink side. The primary S-band receiver on Voyager 2 must have been shut off by fault protection procedures on the spacecraft in April 1978, only a year before its intended collision with Jupiter, when the spacecraft failed to pick up any orders from Earth for a prolonged period. Finally, the backup receiver was turned on. Still, it was discovered to have a faulty capacitor in the phase-locked loop circuits that were supposed to compensate for Doppler shift variations in frequency caused by the Earth's movement. The spacecraft was ordered to switch back to the primary receiver by mission controllers, but this failed once more, leaving Voyager 2 without a method to be controlled from Earth. After a week of no contact, the fault protection algorithms turned the secondary receiver back on, but controllers were stuck. They needed to figure out how to use the spacecraft's faulty backup receiver to keep the mission going. They devised a complicated technique in which DSN controllers guess the uplink frequency based on the projected Doppler shift. The problem is that due to the faulty capacitor, the signal must be within 100 Hz of the receiver's lock frequency, which varies by around 400 Hz per degree as the receiver's temperature rises. It implies controllers must run tests twice a week to ascertain current lock frequency, along with waiting 3 days after uplinking any orders that could modify the spacecraft's temperature to allow the spacecraft dynamically to stabilize. Both X-band and S-band transmitters employ independent exciters and amplifiers on the transmission side. Multiples of these for redundancies, and through the downlink is primarily accomplished using an X-band transmitter. Although this is true, one of the two S-band exciters can be fed into one of two power amplifiers. A robust amplifier/SSA delivers either 6 watts or 15 watts to the feed horn, while a secondary traveling wave tube amplifier/TWTA delivers either 6.5 or 19 watts. The twin X-band exciters employ one of two specialized TWTAs, each of which might provide 12 watts or 18 watts to the high-gain antenna using the S-band exciters as their wavelength reference. The downlink side of the radio's system's redundancy would help save the core objective on both spacecraft. Unfortunately, in October 1987, one of the X-band TWTAs aboard Voyager 1 failed. Voyager 2 had the same problem a little more than a year afterwards. Both spacecraft have been able to switch to another TWTA, enabling Voyager 1 to provide the iconic family portrait of the solar system, which included the pale blue dot image of Earth, and Voyager 2 to return data from its 1989 flyby of Neptune. The radio systems aboard the Voyager spacecraft were developed primarily to enable planetary flyovers. Therefore, they were tuned to send as much scientific information back to the DSN as feasible. Because of the near visits to each outer planet, each spacecraft accelerated considerably during the flybys, where the 10 science equipment on board could produce the most data. Each Voyager had a digital tape recorder, or a DTR, a sophisticated 8-track tape deck to store science information for later downlink to prevent bottlenecks. The bandwidth accessible to downlink science data has also been substantially reduced because of the increasing distance between Voyagers. Data poured at a reasonably fast 115,200 bits per second when the spacecraft performed their initial flybys of Jupiter. Now that the spacecraft are each approaching a full light day apart, data is only coming in at 160 bits per second. Uplinked commands are much slower at 16 bits per second and are broadcast throughout space using 18 kilowatts of power through DSN's 70-meter dish antennas. On the uplink end, the DSN telescopes must dig a signal that has declined to the attowatt level of over the present 23 billion kilometer distance to Voyager 1. On the downlink edge, the DSN telescopes must dig a signal which has gone to the attowatt range. It's a technological triumph that Voyager 1 and 2's radio systems operated while they were still in the middle of their planetary mission. Despite the difficulties of 4 decades in orbit and many system failures, the reality that both spacecraft are still interacting, that's a near miracle. What do you guys feel about NASA's communication? Let us know about it in the comment section below.